Force Introduction. In this lesson, we're talking about what is a force, the four fundamental forces, the force of gravity, everyday forces, action at a distance forces, measuring forces, free body diagrams, net force, force vectors, and finding Fnet. So how does it work? Pause the video and think to yourself, how does this work? How does this rocket ship go up into the air? Now the rocket ship's able to go up because there's a force acting up on the rocket ship, causing it to go upwards. There's another force acting down called gravity, but that force of gravity is less than the force applied by the fuel coming out of the rocket ship. So what's going to happen here? Pause the video and take a look at the four different pictures. So what do we think is going to happen in picture 1, 2, 3, and 4? Now picture number 1, we see the baseball player about to hit the baseball. The bat looks like it's going to be in contact with the ball and it's going to apply a force on that ball, propelling it forward. Picture number 2 here, the car crash, we can see what's already happened. So the red car has crashed into the yellow car, crumpling them and slowing the red car down. That's assuming the red car hit the yellow car and the yellow car didn't back up into the red car. In picture number 3 with the football on the bottom left, you can see the guy in the maroon sweater is hitting the guy in the white sweater. And you can see the guy in the white sweater is going to be falling backwards. At least it looks like he's falling backwards. In this case, it looks like the force of the maroon player is greater than the force of the white player, causing the white player to fall backwards. And then in the fourth picture, looks like we have some kind of hammer or mallet about to hit the egg. The force of the mallet on the egg will most undoubtedly crack the egg. How does it fly? Pause the video and write down, how does this giant chunk of metal stay in the air? Well, there are four main forces acting on an airplane. We're going to have thrust going forward, we're going to have drag going backwards, we're going to have lift going up, and we're going to have the force of gravity going down. As long as this force of lift is greater than the force of gravity, then the plane goes up in the air. As long as the thrust is greater than the drag, the plane will accelerate forwards. So to get the plane off the ground, we need to have a larger thrust, which is going to create this lift, lifting the plane off the ground. Now, why is snow so slippery? Pause the video and write down on a piece of paper why snow is slippery. Now, snow is slippery because the friction between, in this case, the sled and the snow is very low. A low friction will allow it to slide. So these four concepts are going to be looked at in more detail as we go through this lesson. Force overview. So forces act on almost everything. Forces are vector quantities and therefore have a direction. An unbalanced force results in acceleration, compression, stretching, or twisting of objects, and force is measured in newtons with the symbol N, using the components kilogram, meter, and seconds. So what is a force? Pause the video and come up with a definition for a force. After you've come up with your definition, watch number 1 and revise your definition. Now, what is a force? Well, in essence, a force is simply a push or a pull. Sometimes this push or pull results in acceleration, sometimes it doesn't. We need to have a net force to have motion, but a force is simply the push or the pull applied to an object. Check your understanding. State an everyday life example in which a force caused an object to A, decrease its speed, B, become compressed, and C, become stretched. So answer A, B, and C, and then watch videos number 2 and 3. So some examples of decreasing speed might be the brakes on a car. A car's brakes cause it to slow down. Becoming compressed, well, you would have seen in video 2 and 3, when an object hits another object, the second object, and the first object for that matter, become compressed slightly. And becoming stretched, maybe a rubber band. If you stretch a rubber band, it's going to stretch out, and that's due to the force that you're applying on that rubber band. The four fundamental forces. There are four fundamental forces that act in nature. What I'd like you to do is pause the video and put the forces below, so these four right here, in order of relative strength. Make one of the forces have a strength of 1, and the other is a multiple of that. Provide a multiple for the strengths. So set whatever you think is the weakest and make that 1. So say if you think strong nuclear is the weakest, make that number 1, and then you would make the other ones a multiple of that. So if you think gravitational is 10 times stronger, you would write a 10. If you think electromagnetic is 100 times stronger, put 100, and then so on. Put 1,000 for that. Okay, so do something like that on a piece of paper. So how'd you do? Here are the rankings of the four fundamental forces. Gravitational is the weakest. Weak nuclear is 10 to the 25 times stronger. Electromagnetic is 10 to the 36 times stronger. And strong nuclear is 10 to the 38 times stronger. Now let's take a look at them each in detail. Gravitational force. The force of attraction, so not repulsion, between all objects in the universe. It keeps us from floating away into space. It keeps the planets in orbit. And it's a relatively weak force unless one or both of the objects is very large. Its range is infinite, so it works at any distance, but it gets weaker quickly as the distance increases, and that's 1 over x squared. So as we double the distance, be 1 over 2 squared, our gravity would be 1/4 as strong. If we triple the distance, it would be 1 over 3 squared, which would equal 1 over 9. So consider this. You probably think the force of gravity is strong, but your hand and arms are being held towards the ground via gravity, and it's very easy to raise them up. It takes very little energy to defy gravity because it's a relatively weak force. And if you consider those amusement park rides that spin you quickly against the wall, Think about how much more difficult it is to raise your arm on one of those than it is when you're standing still. So gravity, although it's strong to keep us on Earth, it's really not that strong of a force. Check your understanding. How much weaker is the gravitational force between two objects if they are moved from 1 meter apart to 3 meters apart? Number 2. How much stronger is the gravitational force between two objects if the distance between them is halved? So for number 1, how much weaker is the gravitational force between two objects if they are moved from 1 to 3 meters? So what you're doing is you are tripling the distance. So you're going to have 1 over 3 squared, and therefore the gravitational force is going to be 1/9 as strong. Number 2, how much stronger is the gravitational force between two objects if the distance between them is halved? So you are going from 1 to half the distance. So you're going to do 1 over 1/2 squared, which is going to equal to 4 times stronger. So if you increase the distance by 3, it's going to be 1/9 as strong, and if you halve the distance, it's going to be 4 times as strong. Finding the force of gravity, Fg. The units for Fg are kilograms times meters per second squared, and we talked about the fact that that is newtons. Now, one of the main laws of force is force is going to equal to mass times acceleration. Therefore, Fg is going to equal to the mass in kilograms times the acceleration due to gravity. So we're taking the mass of the object times the acceleration due to gravity, which is going to be 9.8 meters per second squared. And keep in mind, you always need to have your mass in kilograms. Check your understanding. If a person weighs 41.6 kilograms, what force of gravity, Fg, will he produce on the ground? So pause the video and answer this question. So we are looking for Fg. Fg is going to equal to mass times gravity. 41.6 times 9.8 equals to 408 newtons. We need to have 3 sig digs in our answer, and we do. Now we also need to have a direction because it's a force. Direction for gravity is always going to be downwards. More specifically, it would be to the center of the Earth, but downwards is sufficient. Check your understanding. A Hummer weighs 3,018 kilograms. What force of gravity, Fg, will it direct towards the ground? What force will the ground direct up to the Hummer? So pause the video and answer this question. Now let's draw it out. There's our Hummer. We said that the Hummer weighs 3,018 kilograms, and we're asked to find what force of gravity will it direct towards the ground. Well, this Fg is going to equal to mass times 9.8, which is going to equal to 3018 times 9.8, and that's going to equal to 29,576.4. We need to have 5 sig digs in our answer, so our final answer should come out to 29,576 newtons down. Now the second part of the question, what force will the ground direct to the Hummer? It's going to be equal to and opposite the force down by gravity. Otherwise, the Hummer will go into the ground or go up into the air. So this will also be 29,576 newtons, but in this case, it's going to be up. The weak nuclear force. The weak nuclear force is stronger than the force of gravity by about 10 to the 25 times stronger. It works at very short distances, so 10 to the negative 18 to 10 to the negative 17 meters, and this is the nuclear level. It causes beta decay in atoms, and it allows the sun to undergo nuclear fusion. It's also responsible for radioactive decay, which allows scientists to date objects using carbon-14, which decays over time at a predictable rate. Electromagnetic force. The force caused by electric charges includes electric force, static electricity, and magnetic force, such as a compass. It's stronger than the force of gravity, 10 to the 36, and can either be attraction or repulsion. The forces generally cancel out, however, so most objects are neutral. It holds atoms, the positive and the negative electrons, and compounds together, and it gets weaker as the distance increases by about 1 over x squared, similar to gravity. So if you stick a balloon to the wall after you rub it on your head, that's electromagnetic force. If you use a magnet to hold nails, that's the electromagnetic force. So what's wrong with magneto's ability? Think about this as you watch the video. So pause right now and watch number 5. And then I want you to answer the question, what's wrong with magneto's ability to move the bridge? Now there's a few things wrong with the scene, but here's my entire explanation. Copy down what you feel necessary. So the magnetic field dissipates according to the inverse square rule, 1 over x squared, and sometimes the inverse cubed rule, 1 over x cubed. As distance increases, the magnetic field becomes extremely weak. Magneto would not have been able to move the bridge because there would be nothing close enough for him to push against, as he can only control the magnetic field around the bridge. So if he's standing on the bridge, like this, he's creating a magnetic field around himself and the bridge. And we'll just draw it like this. This magnetic field needs to push against something in order to raise the bridge off the ground. He can't simply raise the bridge, he needs to push against something else. So that something else needs to be down here or up here. Now, since it's over the water, there's nothing even remotely close for him to push against, even assuming that the entire sea floor is a magnetic substance that he could push against. So that's the problem. This distance right here, again, assuming that he could actually push against the sea floor. The strong nuclear force. It holds the protons and neutrons together. It's stronger than the force of gravity by about times 10 to the 38, and it's a short range force only, 10 to the negative 15, kind of like the weak nuclear force. Forces all around us. So what happens when forces are in equilibrium? Well, nothing. For objects to move, you need to have the Fnet not equal to 0. If Fnet is equal to 0, there's going to be no motion, or at least no change in motion. So for instance, if something is already traveling at 15 meters per second and there's no forces acting on it, so say it's flying in outer space, it will continue to fly at 15 meters per second indefinitely. However, if a force is added to it, like say the object has a rocket booster and that causes an acceleration of the object, then it will change its speed because of a change in the force. Because at that point, the net force is not equal to zero. A good example of this is a tug of war. If these guys are pulling with an equal force that way as that way, there's going to be no movement. So velocity is going to equal to zero. However, if the guys on the right are pulling harder than the guys on the left, then the velocity will not equal to zero, and you're going to get a movement of that rope. So consider the pen on your desk, or the pencil, or the ruler, or the paperclip, or whatever it is that's on your desk. Determine which of the four fundamental forces are acting on it and how. Gravitational, weak, electromagnetic, and strong. So pause the video and list how these four forces are acting on your object right now. Gravitational force. The pen is experiencing a force downwards due to gravity. Weak and strong nuclear forces are affecting the pen because there are many forces acting at the nuclear level, keeping the pen together. And the electromagnetic force is acting because there's an interaction between the subatomic particles on the desk and the pen, also between the molecules within the pen. This helps keep the pen stationary. Everyday forces. In everyday life, we experience the result of the four fundamental forces acting on us and the objects around us. We have given these forces special names based on how they impact us. List as many everyday forces acting on you as you can. Think of the names of the forces you've heard before. So these names aren't going to necessarily be the weak nuclear force, but they're going to be something that you've heard of that relates to force and the motion of objects. So pause the video and list as many everyday forces acting on you right now as you can. So back to our pen example. If there's a downward force of gravity acting on the pen, so we talked about the fact that there is an Fg working on the pen, why is it falling towards the ground? Well, that pen is on your desk, so there's going to be a force opposite to that force of gravity. It's going to be working upwards, and we're going to call that Fn, which is going to be the normal force. So that's one of the forces that are acting on you and the objects around you all the time, the force that's opposing the force of gravity, allowing you to stay stationary. So by definition, the normal force is a force that acts perpendicular to the surface the object is in contact with. It's always equal and opposite. And that makes sense because we think about what would happen if Fn was greater than Fg. Well, that pen would fly into the air because there wouldn't be an equal force. There'd be a net force upwards. So Fn is going to equal Fg. Check your understanding. An average male weighs 84 kilograms. If the man is standing on one leg, what normal force is being produced by the ground upwards on the leg? So pause the video and answer this question. Well, if we have our person, and we're just going to draw him as a box, and we say that he weighs 84 kilograms, that 84 kilograms is going to produce an Fg equal to m times 9.8, which is going to equal to 84 times 9.8, which is equal to 823.2 newtons. So that's the force downwards. So since he's standing on one leg, that entire force is directed up on that same leg. So you're going to have an upward force of 823.2 newtons upwards. Now we need to have two sigmas in our answer. So our final answer is going to become 820 newtons up. Think about it and try. If you push an object across the desk, what will happen? Why does this happen? Does the type of materials matter? Why? Does the mass of the object matter? Why? So what I'd like you to do is pause the video and try number 1, 2, and 3 with any objects that you have around you. Try switching up the materials, both the material that it's sliding on and the material that's being slid, and see what happens. Now what happens when you push an object across the desk? What happens and why? Well, if I push an object across the desk with enough force, it's going to slide. Why does it slide? It slides because our Fnet is not equal to 0, so we get motion out of the object. Does the type of material matter? It certainly does. Heavier objects, rougher objects, they're going to slide slower because they're going to have what's called more friction. And for number 3, I just mentioned, so an increase in mass is going to lead to an increase in friction. And an increase in friction is going to cause a slower motion of the object across the other object. So let's dive more into friction. The force of friction, F little f, is a force between objects in contact. Friction acts always in opposition to motion, and there are two kinds of frictional forces. Number 1 is kinetic friction, or Fk. That's friction where one object moves over another, so there's motion. That's going to be key. And then number 2 is static friction, Fs, and that's friction between two stationary objects, so there's no motion. And you can see right here, our object is moving to the left, or at least that's where motion is trying to go, and our friction is opposing that motion to the right. If we were to change the direction and say that's motion, well, now friction is going to move to the left. It's always going to oppose our motion. Check your understanding. Which direction is friction acting in the following picture, and what kind of friction is acting assuming the car is stationary? So pause the video and answer these two questions. Now the person is pushing to the left, so we're going to say friction is acting to the right. What kind of friction? Well, since it's stationary, it's going to be static friction, because static friction refers to friction involving two objects that are not moving. Check your understanding. Which direction and where is friction acting in the following picture? Number 2, what kind of friction is acting on the wheel, assuming it is in motion? Pause the video and answer questions 1 and 2. Well, we're going to assume that the wheels are turning this way, so he's trying to move that way, right? That's going to be his motion. So So in this case, which direction and where is friction acting in the picture? So as the wheel touches the ground, it's going to be moving that way across the pavement. Since the motion of the wheel is that way, our force of friction is going to act that way. What kind of friction is acting on the wheel, assuming it's in motion? Well, this is going to really throw you off because you probably said kinetic friction because you heard the word motion. But consider a wheel. Every time the wheel moves, that different part of the wheel is going to be touching the ground. So when the wheel is going this way, first you'll get that part touching, and then as the wheel spins, you'll get this part touching and this part touching. The wheel isn't sliding over. If the entire wheel was like this and was just simply sliding over with only one point of contact, then it would be kinetic friction. But since it's rolling and a different part is touching every single time, and they're not actually moving against each other, it's going to be static friction. Tension, Ft. Tension force is a force exerted by strings, ropes, fibers, and cables. The rope held between two teams in a tug-of-war is under tension. Muscle fibers of our body experience tension when they contract. So if you take a look at the tug-of-war example on the bottom left, there's going to be Ft here, there's going to be Ft here, all the way across the rope that's being tugged, that's going to have a force of tension. Same thing with this rope here, we're going to have an Ft right there. Contact versus action at distance forces. The normal force, friction, and tension are all contact forces. In other words, forces that exist when objects are in direct contact with each other. Gravity is an example of an action at a distance force, as the two objects do not need to be in direct contact to feel its effects. So for instance, planets orbiting around the sun. Common forces review. So here are some common forces that you'll be familiar with. Gravity, normal, tension, friction, specifically kinetic and static friction, air resistance, which is just another kind of friction, and applied force. Applied force is the force that we give to all other contact forces. So if you're pushing or pulling something, we're generally going to refer to it as force applied, sometimes written as Fa. Air resistance. The faster you go, the greater the air resistance. As large rocky objects enter Earth's atmosphere, they encounter more air molecules, equals a greater amount of air resistance, which equals increased friction, which increases shooting stars, as the rocks are actually catching fire. So if you think of it like this, the faster you move, the more air molecules you need to push out of your way. If you're running, you're going to push more air molecules out of the way per second than if you're walking. Another analogy is if you're swimming. Think about how much harder it is to walk through water than it is to walk through air. And the reason for that is that you're pushing more water molecules out of the way every second than you're pushing air molecules out of the way, because the air molecules are further apart from each other. So the faster you go, the more air molecules you encounter, the more friction you experience, and the more heat that's generated. The heat generated can be used to ignite objects as they enter Earth's atmosphere. Measuring force. So let's look at how we can measure force. We're going to do that two specific ways, using Newton meters, which is our spring scales, which we have shown here and here, and a force sensor, which is pretty much just a digital spring scale. So what is the relationship between mass and the force of gravity pulling on it? So I want you to pause the video and answer the question, what is the relationship between mass and the force of gravity pulling on it? Well, mass and Fg are directly proportional to each other. As mass increases, Fg increases. And we know that from our equation we talked about before, F is going to equal to mass times acceleration. If we increase the right side of the equation, we're going to increase the left side of the equation. So more mass, more force. What force does the cup exert downwards? So I will look at the Newton scale and try to figure it out. The answer is 4.5 newtons downwards, and we can see that by looking at the Newton scale. You can see right there, the little bar here comes in at about 4.5. So that's how we're measuring that number. System diagrams and free body diagrams. A system diagram is a sketch of all the objects involved in a situation. A free body diagram, or FBD, is a drawing of a single object that shows only the forces as vectors acting on the object. Keep in mind, we always need to indicate the positive x and y directions. All force vectors need to be included in a free body diagram and labeled, with their lengths proportional to the magnitude of the force. So for instance, this would be a smaller force than this. Now our system diagram, like we were talking about, is a full image of everything that's involved, but it's really just more of a picture of what's happening. So if we're talking about a volleyball being pushed upwards, we're going to show the hand and the volleyball. And this isn't something that's going to give us a lot of information. So typically we're going to refer to our free body diagrams, in which case we're going to have the object, which is simply represented by this object right here. We're going to have our Fn, we could also say F applied, and we're going to have our Fg, which is working downwards. And don't forget, we have our positive y value right there. We don't need to have a positive x value because in this case it's only going to move up and down. Check your understanding. You toss a 100-gram ball vertically upward. Draw a free body diagram of the ball just before it leaves your hand. So pause the video and answer this question. Here's our free body diagram. You're going to see we have the mass label. We have our object represented by this black square. We're going to have an Fn, and again, we could also write this as F applied, upwards. And that vector is greater than the Fg, because we're assuming the ball is moving upwards, because it does say it's moving upwards. And we're going to say up is positive, so we're going to say our positive y is upwards. Check your understanding. A child is pushing with a horizontal force against a chair that remains stationary. Draw a free body diagram of the chair. So pause the video and draw this free body diagram. So here's our free body diagram. We have our static friction because it's stationary. We have our force applied going in the opposite direction, and you'll notice that the vectors are going to be even. They're going to be the same length because the chair is stationary. So the force applied is equal to the static friction. We need to include our Fn, And that is going to be the same length as our FG because the chair isn't flying into the air or going into the ground. And then we're going to state that up and to the right are positive, and that's represented by our image up here. Check your understanding. Draw a free body diagram for the following. A, your textbook resting on a desk. B, a tennis ball falling through the air from the server's hand, neglect air resistance. And C, a fully loaded dog sled moving at a constant, slow pace along a flat, snowy trail while being pulled horizontally by the dogs attached to it by a rope. So pause the video and answer these three questions. A, your textbook resting on the desk. So you'll notice we have the textbook represented by this black square. We have our FN, our FG, and we have our resting textbook. So our FS length is going to be equal to our FA length. And again, our FN is going to be equal to our FA. We have our positive represented up here. So why do we have our FA and our FS? Well, the force applied, FA, is created by any small air currents in the room and is offset by the static friction. That's why the book doesn't just slide small amounts here and there. B, a tennis ball falling through the air from the server's hand, neglect air resistance. The key here is falling through the air. It's not being pushed up anymore. So the only force acting on the tennis ball is FG, since we said neglect air resistance. We're saying up and to the right is positive, and there's our complete FBD. C, a fully loaded dog sled moving at a constant, slow pace along a flat, snowy trail is being pushed horizontally by the sled owner while being pulled horizontally by the dogs attached to it by a rope. So we're going to say up and to the right is positive, so that's represented here. We're going to have an FN and FG offsetting each other, so these are going to be the same because the dog sled isn't going into the air or into the ground. And we're going to have two other vectors. We're going to have an F applied going to the right. That's representing both the sled owner pushing and the dogs pulling. And then we're going to have our FK going to the opposite direction, in this case to the left. Now our left is going to equal to our right, and that's maybe where you got tripped up. One key thing in this question is that it's moving along a constant pace. If it's a constant pace, then we know our Fnet is equal to 0 because our acceleration is equal to 0. Thereby, it's a constant pace. So make sure that your vector for FA is equal to the vector for FK because they're canceling each other out. That does not mean that the velocity is 0. Velocity is 0 if it was stationary to begin with. Then its velocity would be 0 because its Fnet would be 0. But since it's moving at a constant pace, its velocity is not equal to 0, but its acceleration is 0. Let's review net force. Net force is the total of all the forces acting and is written as Fnet. It is also referred to as the sum of the forces, which can be written as sum of forces, which is shown right here. If we write sum Fx, that's the sum of the forces in the x direction. And if we write sum Fy, that's the sum of the forces in the y direction. So for example, if you have a 3 Newton force to the right and a 2 Newton force to the left, the net force, or the sum of the forces, is going to equal to 1 Newton to the right. This is why it's important to designate a positive x and a positive y value. By doing so, we can solve Fnet by equaling it to plus 3, because it's going to the right. We said right was positive, plus negative 2. Since it's going to the left, that would be a negative number. So plus 3 plus negative 2 equals plus 1. Check your understanding. A weightlifter holds a weight above his head by exerting a force of 1800 newtons up. The force of gravity acting on the weight is 1600 newtons down. Draw a free body diagram of the weight and state the net force at that instant. So pause the video and answer A and B. So for A free body diagram is going to be represented by a little box. There is a 1600 Newton force downwards and a slightly larger 1800 Newton force upwards. And that's all the forces acting on the weight. And the last thing we need to do is state our positive direction. We're going to say up is positive. B, state the net force. The sum of the forces is going to equal to 1800 plus negative 1600. 1800 plus negative 1600 is 200 newtons up. Check your understanding. Team red is pulling on the rope to the right with a force of 5 newtons, and team blue is pulling to the left with a force of 7 newtons. What is the net force? Pause the video and answer this question. So the net force, if we assume that right is positive, is going to be plus 5 plus negative 7, which is going to equal to negative 2. Since we said right was positive, the Fnet is going to equal to 2 newtons to the left. Check your understanding. What is the net force in the following situation? Pause the video and find the net force. So we're going to say that right and up are positive, and we're going to notice that 250 up is going to cancel out the 250 down. So there's going to be no net force in the y direction. So the only thing left is the x. So we're going to say the sum of the forces in the x direction are going to equal to 50 plus negative 350, and that equals to negative 300 newtons. Since we said right was positive and we get a negative number, so the sum of the forces are going to equal to 300 newtons left, and that's our final answer. Force vectors. In order to deal with force vectors that point in odd directions, we will resolve the vectors into components of the coordinate system. And by odd directions, I mean this guy here, that's pointing to the right and upwards. So we're going to break it down into the x and the y components. So if f is equal to 100 and the angle of inclination is 30 degrees, like we see down here, we can break our vector into the f and y components. F of x is going to equal to 100 times cos 30, which is equal to 50 newtons. And f of y is going to equal to 100 sine 30, which equals to 87 newtons. And if we're looking at multiple vectors acting on an object, we can find the sum of those forces using this method. Check your understanding. In hitting a volleyball, a player applies an average force of 9.9 newtons, 33 degrees above the horizontal, for 0.01 seconds. The force of gravity on the ball is 2.6 newtons down. Determine the net force on the ball as it's being struck. I'd like you to pause the video and try this question. So let's draw it out. We're going to represent the ball with this a circle, and we're going to say it's going to be hit at an angle of inclination 33 degrees above the horizontal, and it's going to be hit with a force of 9.9 newtons. The time here is just a red herring. It doesn't actually tell us anything that we need to know, so we're going to ignore it for now. The force of gravity on the ball is 2.6 newtons, and we're asked to find the net force acting on the ball. So we need to break it into our components. We need to find the sum of the x's, and we need to find the sum of the y's. We are going to say that right and up are positive, and for the x, we're going to take a look at, first of all, this component here, and then there's no component for the 2.6. So the sum of the f of x is going to equal to 9.9 cos 33, which equals to 8.3 newtons. So now we're going to find the f of the y's. That's going to include this guy going up and this guy going down. We said up was positive, so the first one, the 9.9 sine, because it's opposite, 33, is going to be positive, but then we're going to subtract, or we're going to add the negative of this 2.6 going down. And it's just 2.6 because there's no angle. So if you have 9.9 sine 33 and you subtract 2.6, you get 2.79 newtons. Now to find the sum of the forces, we need to add our components. So we're going to take our x components to the right, so it's positive 8.3. We're going to go up 2.79, and we're going to find the sum of these by taking the hypotenuse, which is that guy right there. So the sum of the forces is going to equal to the square root of 2.79 squared plus 8.3 squared. And that equals to 8.76 newtons. We need to find the angle that this makes right here. So we're going to say theta is going to equal to tan minus 1, opposite, which is 2.79 divided by 8.3. And that gives us a theta of 18.6 degrees. Now, based on what we've talked about here so far, we're going to say that's 18.6 degrees above the horizontal. Now, we're not quite done because we need 2 sig digs. So our final answer is going to be 8.8 newtons, 19 degrees above the horizontal. And that's our final answer. Check your understanding. A sailboat is secured to a dock with 2 horizontal ropes. A wind is blowing offshore. The tensions in the ropes are F1 equals 48 newtons, east 16 degrees north, and F2 is 48 newtons, east 16 degrees south. A. Use a vector diagram to determine the sum of the tension forces in the 2 ropes. And B. Assuming that the net horizontal force of the boat is 0, determine the force of the wind on the boat. So I'd like you to pause the video and answer A and B. Okay, so let's draw out our scenario. There's our boat, and our boat is going to be secured to the dock using 2 ropes. There's our dock, and both angles are 16 degrees. So it's going to look something like that. So what we need to do is we need to find the sum of the x and y components. Well, real quick, we can determine that where we have one y going up and one y going down. And since both of the forces are 48 newtons, they're going to cancel each other out. So the sum of the y's is going to actually equal to 0. All we really need to focus on are the x's. If we take the sum of the forces in the x direction, we can figure out the sum of the forces on the boat. We're going to say that x is positive, and we'll say that y up is positive. So some of the forces in the x direction are going to be 2 forces that are both acting in this direction. We're going to say it's 48, and it's both are going to be cos 16 plus 48 cos 16. And that equals to 92 newtons. And the direction we're given is east. And that's our final answer to 2 sig digs, which we need. Assuming that the net horizontal force on the boat is 0, so we say that the net x is 0 total. So that would be the sum of the fx total going both ways is equal to 0. Determine the force of the wind on the boat. Well, if we get a force going this way of 92 newtons, and the boat is not moving, then that means there must be a force equal and opposite going that way at 92 newtons. So the answer to B would be 92 newtons west. Check your understanding. Draw a free body diagram and determine the net force. At a particular instant, a soaring bird traveling east is subject to an upward lift of 3.74 newtons, a downwards gravitational force of 3.27 newtons, and a horizontal air resistance force of 0.354 newtons left. Now we're going to say left is also equal to west. We're going to need that information in this question. So what I'd like you to do is pause the video and determine the free body diagram and the net force. So if we draw a bird and we say that that way is east and that is positive, and east is also to the right, we know that we're going to get an upward force of 3.74 newtons, a downwards gravitational force of 3.27 newtons, and we're going to get a horizontal air resistance force of 0.354 newtons, in this case to the left. So we need to find the net force. We're also going to say that up is positive, and that would be north in this case. So we need to find the sum of the forces in the x and the sum of the forces in the y. In the x direction, since we said right and east are positive, we're going to have negative 0.354, and then we're going to add 0 and 0 because these guys don't have an x component. So it's going to equal to negative 0.354 newtons. In the y component, we're going to have 3.74, plus negative 3.27. And that equals to 0.47 newtons. Now we said north was positive and so was east. And we got a negative for x and a positive for our y. So we're going to go left 0.354 and we're going to go up 0.47. And we're going to find the hypotenuse. The hypotenuse is going to be the sum of the forces. So the sum of the forces is going to equal to the square root of 0.47 squared plus 0.354 squared. And that equals to 0.588 newtons. We need to find theta. Theta is going to equal to tan minus 1, 0.47 divided by 0.354. That equals to 53 degrees. So our final answer to 3 sig is going to be 0.588 newtons west, 53.0 degrees north. Check your understanding. Draw a free body diagram and determine the net force. A long jump contestant experiences at the instant of landing a gravitational force of 538 newtons down and a force applied by the ground to the feet of 6,382 newtons, 28.3 degrees above the horizontal and towards the jumper. So pause the video and answer this question. So let's draw a free body diagram. So our contestant has a gravitational force of 538 newtons down and a force applied by the ground to the feet of 6,382 newtons, 28.3 degrees above the horizontal and towards the jumper. So what that's going to look like is something like that, 6,382. So what we need to do is we need to find the net force. We have our free body diagram, and we could rewrite it properly. So it looks something like this. We're going to have a force going up, so that's towards. We're going to say that is going to be our motion, and that's going to be positive. So it's going to be towards and above the jumper, 28.3 degrees. Now we're going to have our force of gravity down. And you should try to make the vectors as proper as possible, but this isn't really going to be the case because we just have such a discrepancy in our forces. So 6,382 and 538. So let's find our net force. We said right was positive, we're also going to say up is positive. So let's draw our y vectors. We're going to have one y vector here and one y vector here. We're going to have an x vector going to the left. So we find the sum of the forces in the x direction first. We're going to have minus 6,382 cos 28.3. And that equals to negative 5,619.2. And then our y is going to be positive 6,382 sine 28.3 minus 538. And that equals to 2,487.6 newtons. So now we're going to draw our triangle. We're going to go to the left, 5,619.2, and we're going to go up 2,487.6. And then we're going to draw the hypotenuse, and that's going to be the sum of the forces. The sum of the forces is going to equal to the square root of 2,487.6 squared plus 5,619.2 squared. That equals to 6,145.2 newtons. We need 3 sig digs in our answer, so our final answer is going to be 6,150 newtons. We need an angle. Our theta right here is going to equal to tan minus 1, opposite, which is 2,487.6 divided by 5,619.2. That equals to 23.9 degrees. So our final answer becomes 6,150 newtons. I'm going to call it 23.9 degrees. We're going to use the same as we said right here. So we're going to say above the horizontal towards the jumper. Check your understanding. The mass of the cart is 60.6 kilograms. Find all the forces and the net force. So pause the video. I want you to solve for Fn and Fg. Okay, now this isn't as straightforward as you might think. The Fg is pretty basic. Fg is going to equal to mass times gravity, which is going to equal to 30.6 times 9.8, which equals to 299.88 newtons. We need to have 3 sig digs in our answer, so our final answer is going to be 3.00 times 10 to the 2 newtons. Now Fn is not equal to Fg, and the reason for that is this guy right here, our F applied. This F applied is going to take some of that force away. Remember, we need to have the net force in the y direction equal to 0. To get that, we're going to need to add up all the Fy's. Sum of the Fy is going to equal to the component of Fa, so it's going to be 95 sine 22 plus Fn, and those together are going to equal to Fg. And we just found out what Fg was. So 95 sine 22 equals to 35.59. Then we say plus Fn equals to what we just found. We're going to use the whole number, 299.88. We're going to rearrange. We're going to say Fn is going to equal to 299.88 minus 35.59, and that equals to 264.3 newtons. Now I said previously that we need 3 sig digs. We actually need 2 sig digs in our answer, so we'll go back and fix the Fg in a second. But Fn is going to be 260 newtons up, and our corrected Fg shouldn't be 3.00 times 10 to the 2. It should be 3.0 times 10 to the 2 newtons down, and that's our Fg final answer. Now, the last thing we need to find is the Fnet. The Fnet is going to be the sum of the forces in all the directions. In this case, we know the sum of the Fy's is going to be equal to 0. We just figured that out, right? It's not flying into the air. It's not sinking to the ground. So the Fy's are 0. So the only thing we need to be concerned with are the Fx. So Fx is going to include this guy right here and this guy right here. So some of the F's are going to be the 95 cos 22. That's this guy right here. And we're going to say that right and up are positive. Then we're going to say minus 25. So 95 cos 22 minus 25 is going to equal to 63 newtons. And we get a positive value. So the sum of the forces is going to be 63 newtons to the right. And that's our final answer for the sum of the forces. Ramps, finding Fnet. So if you recall, when analyzing a problem involving forces acting on an object, you must find the sum of all the forces acting on that object. And to do so, we always make our axes. We say a positive x and y like that. When we're dealing with a ramp, we still need to have this positive x and y value, but we have a ramp. So the easiest thing to do, instead of drawing our axes like this, as we normally would, we're going to rotate our axes fit the ramp that it's on. So in this case, that would be our positive x and y value. And by doing that, it's going to make our math a lot easier. So let's try. Check your understanding. A child pulls a sleigh up a snow-covered hill at a constant velocity at an angle theta with a force parallel to the hillside. Draw the free body diagram of the sled. So the first step is we're going to rotate our axis to align with the ramp, like we have right here. We're going to equate the ramp angle with the angle formed by the components of Fg. And we're going to see what that means in a second. And then we're going to include all the forces. So here's our free body diagram right here. So we rotated our axes. We got that. We equated the ramp angle theta with the angle formed by the components of Fg. And that's what we did right here. So you can see the components of Fg. Fg is located right here. And the components of Fg are going to be Fg cos and Fg sine, both with theta, same angle that the ramp is on. And then we include all the forces. Ft could also be called force applied. We have Fn, and Fn on our ramps is going to equal to Fg cos theta. It's the one that's exactly opposite to it. And then we have Fk, the kinetic friction. So when doing your diagram, make sure you turn your axes and make sure that your theta angle is equal to the angle that the ramp makes. Check your understanding. Fill in the blanks and determine the net force in the following situation. The object has a mass of 35.7 kilograms. Hints. Fn doesn't equal to Fg. We just talked about that, right? Fn is going to equal to Fg cos theta. Fn is a component of Fg, and that's what we're talking about right there. The ramp angle theta equals the angle formed by the components of Fg. And lastly, the ramp angle theta equals the angle formed by the components of Fg. Now to answer this question, it's going to be easier if we have a little bit more space. So here's the same question. And what we're going to do is we're going to break our Fg into its components, and we're going to find out all the forces acting, and then we're going to solve for the net force. So to find the components of Fg, we're going to break our Fg into its component parts. So this guy right here is going to be Fg cos theta. This guy down here is going to be Fg sine theta, and theta is going to be right here. Theta is going to equal 15 degrees because the angle of the ramp is 15 degrees. Fg, we can solve right off the bat. Fg is going to equal to our mass, which is 35.7 times 9.8, which is equal to 349.86 newtons. To find Fg cos theta, we're going to take 349.86 times cos 15 equals to 337.94 newtons. And to find Fg sine theta, we're going to take 349.86 times sine 15, 349.86 sine, and that equals to 90.55 newtons. Now we talked earlier about Fn not equaling Fg, but instead equaling Fg cos theta, and we found that out right here. So Fn is going to equal to 337.94 newtons, and we have all our blanks filled in. Now we need to find the net force. Keeping in mind our x and y axes looks like this, and we know that the sum of the y's is going to equal to 0 because the object isn't flying off the page. So what we really need to concern ourselves with are the x's. So the sum of the forces in the x direction are going to include 4, 5, 5. We're going to subtract our force of friction, which is 150. We're going to subtract this force right here going down the ramp, which is 90.55. And that's all the forces acting on this object in the x direction. So when you take 455 and you subtract 150 and 90.55, you get 214.45 newtons. Now, since the positive value is going to be up the ramp, so we would say up ramp. Now we need two significant digits in our answer. So our final answer is going to become 210 newtons up ramp. And we have two significant digits because we have two sig digs right there and there. And that's our final answer, 210 newtons up the ramp. And that concludes our force introductory lesson.